Hello everyone. So the purpose of this video is to wrap up notes number 14 on series. This is intended to be kind of a one-size-fits-all video to complete these notes, but I know different sections are at slightly different points in the notes, so some of what I talk about here you may have seen before. If so, please feel free to skip ahead in the video to wherever you need to be. Alright, so with that, let's get started. I'm going to begin by finishing up the topic of telescoping series. All right, so what were these about again? So the basic idea of a telescoping series is it's a series whose terms kind of self-cancel with each other in a kind of staggering sort of way. So future terms cancel with previous terms and that kind of construction. So a good first example of such a thing to keep in your mind when thinking about these is maybe this series. So 1 minus 1/2 plus a half, minus a third, plus a third, minus a fourth, plus a fourth, and so on. And so the idea was a lot of the terms cancel with their immediate neighbors. So minus 1/2 cancels with plus a half, minus a third cancels with plus 1/3, and so on and so forth. All right, so we already did a number of examples covering these, and the general construct that we encountered was we would have something that looks like this. Sigma sum n equals 1 to infinity of, oh, I don't know, something like 1 over, say, n plus 2 minus 1 over n plus 1, something like that. So a lot of times a good giveaway for a telescoping series doesn't always work, but a good trick to recognize a telescoping series as a formula is if you have the sigma sum of two terms being subtracted from each other. So something like this construction right here. All right, so we saw a number of examples. One that looks kind of like this, another one involving natural log, another one involving cosine. So I have one more to show to you guys, which seems to break the mold a little bit of what we've been doing so far. So let's consider this series. Sigma sum n equals 1 to infinity of 2 divided by n squared plus 2n. All right, so like I said, this kind of breaks the mold of what I just said. This is not a sigma sum of something minus something, it's just a single fraction. And indeed, if you were to go and list out some of the terms, I don't think you would find any self-cancellation immediately present. But nevertheless, I argue that this thing is, or can be converted into, a telescoping series, so we can find its partial sums and all the rest of it. So what are we going to do? How can I make this look something like that? Well, one thing, so we've seen something kind of like this before, right? Where we wanted to go and turn, say, a single fraction into a sum or difference of multiple fractions. So maybe it'll be a little more clear if I rewrite this like this. If I factor out the denominator. N times n plus 2. If you recall, there's a way to go and break this up into two separate fractions, and it goes by a name that is still likely to induce nightmares: partial fractions. Yeah, so we can actually use partial fractions here to make this, this formula resemble this a bit. Well, pretty much resemble this very closely. So we already spent a whole section, or a whole unit, I guess, in a sense, covering partial fractions, so I'm not going to go through the entire procedure. If you need a refresher on that, you know where to look. But I'll just go ahead and skip to the end. So horrible things happen in here. So at the end of it all, it turns out that the partial fraction decomposition of that formula turns into sigma sum of 1 over n minus 1 over n plus 2. All right, so now we're in a position that of the previous examples that we've seen before. So we know the drill. Let's go and write out the first 3 or 4 terms of this series. All right, so n equals 1 comes first. So I think I'm going to have 1 minus 1/3, I think. And then I think we have a 1/2 minus a 4th. And the positive terms, the denominator is just going to increase by 1 each time, and the negative terms do the same thing. So I think the next one up is going to be a plus 1/3 minus a 5th. Oops. No, yeah, that's correct. And plus a 4th minus a 6th. And maybe one more for good measure. Plus a 5th minus a 7th. And it just keeps on going from there. But in usual fashion, we are just going to restrict our view to just this first, I think, 5 mini terms. So 5 groups of 2. So this is S5. All right, so let's go and see what cancels with what. So we have then, okay, so we have a minus 1/3 canceling with the plus 1/3. We have that. 1/2, I think, is fine. It doesn't cancel with anything. Minus a 4th cancels with plus a 4th. Minus a 5th cancels with plus a 5th. And I don't think anything else cancels away. All right, so now let's go and find out here what, out of these surviving terms, which ones are persistent and which ones are really doomed to be canceled at a future term, that are only surviving here by a fluke of me stopping at S5 instead of at S something else. All right, so 1 is 1 likely to be canceled by anything else in the future. I don't think so, because again, these denominators are on the increase. If we're at, the only thing 1 could be canceled with is a negative 1, and we're never going to get negative 1 again. The negative fractions are going minus a 5th, minus a 6th, minus a 7th. We're never getting back to 1. So this one is going to persist. And I think the same story goes with the 1/2. So 1/2 can only be canceled by a negative 1/2, but the lowest denominator negative term we've got is a minus 1/3, and they just go on to the increase from there. So indeed, this one is also going to persist. Don't think that's the case with these two, right? So minus 1/6 is it doomed to be canceled later on? I think yes. Over here we have a plus 1/5, but the very next term after this minus 1/7 is going to be a plus 1/6. So this one is going to be canceled away later. So I'm going to call it a variable. And I think the same story goes with the minus 1/7. That will be canceled 2 terms down, which is the time it'll take for the plus 1/5 to turn into a plus 1/7. So yep, that one is eventually doomed. So I will label that also as a variable. All right, so out of this, let's go and write a formula for S5. So S5 is going to have the 2 persistent terms. It's going to have 1 plus a 1/2, and we're going to have minus a 6th, which I will try to write in terms of the formula that I started with, so I can kind of keep track of where the where did the 1/6 come from. So this 1/6 is coming from the second component of the next to last term. So this is the 5th term. This pair of terms is the 5th term in this series. This is the 4th term. So this is the 4th term, second component. So I will write that then as 1 minus 4 plus 2. Where this 4 is a stand-in, you can think of it as a representative of the second to last index. And in this case, the minus 1/7, it's the same thing. It's the second component, but of the latest term, the 5th term in the series. So this will be minus a 1 over 5 plus 2. All right, and so the idea is there's nothing special about the specific numbers 5 and 4. They are just representatives for the latest term and the second latest term. So then that tells us then that the general formula for the partial sum sequence is going to be 1 plus a half minus 1 over, I guess, n minus 1 plus 2, that's n plus 1. And this one will be minus 1 over n plus 2. All right, so very good. We got the partial sum formula. And of course, that enables us to find the total sum. If we take n to infinity, what's going to happen? Well, both of these terms are going to go to 0, right? So we get then that the total sum, the actual sum of the series that we started with, the sum of all infinitely many terms, is going to be just 1 plus a half, or 3 over 2. All right, so that's a wrap-up of telescoping series for you guys. So there's one other type of series left to cover, and those are the geometric series. All right, geometric series. All right, so what is a geometric series? Well, its defining characteristic, so first of all, let me go and write a generic series out. So let's say we have sigma sum n equals 0 to infinity of a sub n. So the defining feature of a geometric series is that the ratio between successive terms is always a constant. So that is to say, if you take the next term and divide it by the current term, wherever those two terms are in the series, this thing will always equal some constant r. I suppose it's called r for ratio. All right, so it turns out then that a geometric series can be expressed in the following form. So geometric series can be represented as sigma sum n equals 0 to infinity of a times r to the n, where both a and r are constants. So a actually stands for the initial term, and r is this ratio. So it turns out geometric series are a nice kind of series because we are actually able to find the total sum of them pretty easily. It follows a relatively simple formula. So the sum of a geometric series turns out to be this a coefficient divided by 1 minus r, the ratio between successive terms. Although there is a bit of a catch. So not all geometric series converge. So it turns out they only converge if and only if the magnitude, the absolute value of r, is strictly less than 1. Or to put it another way, if and only if r is strictly in between -1 and 1. So if r is bigger than 1 in magnitude, this series is going to diverge. Which kind of makes sense if you think about it. So if r is something bigger than 1, then the successive terms are just going to increase and increase and increase. If you raise something bigger than 1 to higher and higher powers, it is just going to blow up and blow up and blow up. And so the divergence test will go and tell you right away if the terms are very much not going to 0, so this series is going to diverge. Although the special thing about geometric series is it turns out if r is strictly less than 1 and the terms do go to 0, then in the case of geometric series only, that's enough to conclude, yeah, it converges, and this is what it converges to. All right, so let's go ahead and do an example then. So I think example 5 is what's next. All right, so what we're doing here is I'm going to give you some series, and our job is to find out, does the series converge or diverge? And if it converges, let's find what the sum is. So here's the first one. So let me write it out. Actually, so what I think I'm going to do here is I'm going to go slightly out of order of the notes that are posted. I'm going to go and do the second example in example 5 first. So let's consider this one. Sigma sum n equals 0 to infinity of 5 times 4/3 to the power n. All right, so in this case, what do we have going on here? So this thing matches up with the general form of a geometric series pretty closely. This is going to be our A, and that's going to be our R. And in this case, I think it's pretty clear that R is greater than 1. So in that case, what that tells us is this series diverges. Four-thirds is bigger than 1. You raise it to bigger and bigger powers. The terms are going to go to infinity. So the series is certainly not going to converge. All right, so that one is maybe a bit of a boring example. So here's one maybe a bit more interesting. So in this case, I'm not going to write it out as a formula. I'm actually going to write out the first few terms of the series and just infer the pattern off of that. So 5 minus 25 over 6 plus 125 over 36 minus 625 over 216. And so on and so on and so on. All right, well, in order to go and find the sum of this, well, okay, so first of all, before we even jump into what is its sum, we had better check if this thing is even convergent or not. So to do that, the thing that decides convergence or divergence, well, and the sum for that matter, is always this R, the ratio thing. But in this case, we don't have the formula to really go by to tell us, well, what is the formula in this case? So we can try to construct it. I think you can see the kind of what the pattern is in this case. We have 5 and then 25 and then 125 and 625. So it looks like the numerators of my terms are just successive powers of 5. So like 5 to the n or something like that. And whereas the denominators seem to follow powers of 6, 6, 36, 216, 6 to the power n, or maybe 6 to the power n minus 1 or something like that. They're slightly out of phase with each other. So you might be able to construct something off of that, but the good news is we actually don't have to. If you recall what both the A and the R, the constants that determine the formula for a geometric series, if you remember what these things conceptually represent. So if you recall, R is just the same, well, originally what it was defined to be, it is excuse me, it's the ratio between any successive terms of the series. Any successive terms. So one way that I can find what R is, if we're already convinced that this is a geometric series, is I can just take the ratio of any two terms, and that will be my R value. So naturally, I will pick the ratio of the two simplest terms. So we'll take this term, negative 25 over 6, and divide it by 5, the ratio of these two terms. So if I do that, I get negative 25 over 30, I think, which gives me a negative 5 over 6. All right, so there we go. We have R. So what about A? So if you remember, the way that I explained what A is A is actually the initial term in the series. So one thing that I didn't mention explicitly, which is maybe worth pointing out, is the formula for a geometric series. It turns out they like to start with index n equals 0. So far we've been dealing with n equals 1, but geometric series prefer to start at n equals 0. So in that case, you can see why A would be the initial term. The initial term corresponds to n equals 0, and if I plug in 0 into this, r to the 0 is just going to be 1, so that vanishes, and we're just left with A. So A is whatever the first, or maybe I should say initial, because it's, I guess, actually the 0th term, but it's the initial term in the series. So A is just going to be 5. All right, so there, without even having to do any special analysis of what's the pattern going on with these numerators and denominators, we can already decide that the formula for this geometric series is going to be 5 times negative 5/6 to the power n. All right, so does that converge or diverge? So I think this one's going to converge, right? So minus a 5/6 in absolute value is equal to 5/6, which is definitely less than 1. So yep, we've got something that converges. So in that case, we should be able to write out a formula for the sum. All right, so we can do that. So the sum of the series is therefore going to be, as a reminder, it's a divided by 1 minus r. So my a in this case is 5, and my r is a negative 5/6. So I'm going to have 1 plus 5/6 because of a double negative. All right, so I think what we get then, we go and put that all together. I think this winds up being 30 divided by 11. All right, so so far so good. So let's keep on going then. So here's another example for you guys. Let's consider sigma sum n equals 1 to infinity. So important to note, this is not 0 anymore. Of 4 divided by 3 to the power 2n. All right, so once again, this is not written in the normal form of a times a constant to the power n. So is there any way we can turn this formula into something that looks like that? So I think we can do that with a little bit of algebra trickery. That's the usual answer to almost every problem, isn't it? So I have sigma sum 4 divided by, let's write this as 3 squared to the power n. So I can do that because if you raise a power to a power, that's the same as multiplying them. So just that exponent rule. All right, so if I keep on going, let me rewrite 3 squared as 9. So this is 4 over 9 to the n. And so I can play a few more tricks. So let me separate the 4 away from the fraction. So I can write this then as sigma sum 4 times 1 over 9 to the n. But 1 is the same as 1 to the n, so I can write it out like that. And then I can factor out the these two n's from the division into one single fraction to the power n. So 4 times 1/9 to the power n. All right, so there we go. So yeah, this is just another way you can go and rewrite a formula that doesn't look geometric into one that very much does. But again, if this to you seemed a little bit weird or it didn't make a whole lot of sense to you, don't forget that you can always play the trick of finding a and r more concretely, I guess, by just plugging in, say, the... well, okay, so you have to be a little bit careful here. So if you want to do it the other way, where you're wanting to find a and r manually, you should actually start with n equals 0, even though the series here says it starts at n equals 1, because a is always supposed to refer to the 0th term, technically. So what you would do in order to find a is you would plug in 0 in for n, and so you would get 4. And if you want to go and find r, what you could do is, again, take the ratio of any two successive terms. You could plug in n equals 1 and n equals 2, and take the ratio of the second one minus the second one over the first one, or you could do the first one over the imaginary 0th one, something like that, and you should get 1/9 in either case. But at any rate, however you get it, we can rewrite our series as this. And so does this converge? I think yes. So 1/9 is less than 1. So we should be able to write out the sum of this series, or or can we? So maybe not. So one issue here is, again, I said geometric series really prefer to start at n equals 0, and the formula for computing the sum, the formula a divided by 1 minus r, that assumes that you are starting from n equals 0. So in this case, we're not starting from n equals 0, so we can't quite use it. But again, it seems kind of annoying because we're really very close. So how can we handle this? So there's a couple of ways you can deal with it. I think one of the most straightforward ways to do it is like this. So really what I've got here, by starting at n equals 1, I'm basically taking the series, the version of the series where we started from 0, and I just threw away the 0th term. Right, so one weird way you could compute this series is you could go and compute the series n equals 0 to infinity and just subtract off whatever the 0th term is. And if you remember, the 0th term, or the initial term, is just the same thing as a. So really what I could do is I could just go and find the sum of the series, pretending that it started from n equals 0, and then I just have to remember, oh wait, I need to adjust this by subtracting off the 0th term, which is not actually there. So that's what we'll do. So for this we can find the form. We do have a formula for. This is going to be a, which is 4 in this case, divided by 1 minus a ninth. And then the only thing I need to do is adjust this by subtracting off a, which was 4. All right, and so I think if you want to go ahead and simplify it, it turns out to be rather nice. It turns into just 1/2. All right. Okay, so here's another one for you guys. Let's take a look at this one. So we have sigma sum n equals 2 to infinity this time of -1 to the power n times 2 to the power n plus 1 times 5 to the power -n. All right, so there's a lot of stuff going on here, so the goal is still the same as last time. We want to rewrite this somehow in the form a times a constant to the power n. So how can we do that here? Well, we can use the same general sort of strategy that we used here. So I didn't say it explicitly, but kind of the idea here is we want to go and make every factor of the formula just have a single positive power of n in it, and we'll factor out anything, transform the expression any way that we can in order to get the factors to look like constant to the power positive n all by itself. All right, so let's go ahead and do that. So -1 to the n is actually already all set. We don't need to do anything to that. So I want to rewrite 2 to the n plus 1 as just 2 to the n. So there's a way to do that. I can write this as, well, maybe I'll write it down below. I can write that out as 2 to the n times 2. And similarly over here, I have 5 to the power -n. I want that to be 5 to the positive n, but that can be accomplished by taking 1 and dividing it by 5 to the n. Raising something to a negative exponent, you can make the exponent positive if you put it in if you take the reciprocal. All right, so evidently I can go and rewrite this then as -1 to the n times 2 to the n times 2 times 1 over 5 to the n. All right, so now what I'm going to do is I'm going to group together any factor that has an n in it on one side of the expression and any constants on the other. So I think then the only constant I'm really going to wind up having is just this 2. So we have 2 times, I think, -1 to the n times 2 to the n, all divided by 5 to the n. All right, and now we'll just factor, well, quote unquote factor, out the exponent of n. Right, so we get 2 times, and if I factor out the n, then all these multiply, so I think that's just going to be a negative 2/5 to the power n. All right, and a negative 2/5 in magnitude is definitely less than 1. So this series is going to converge, and so we can find the sum, again, using that formula, although here we have to be a bit careful again, because we're starting from n equals 2 in this case. But the game is not much different. If I want to go and find the sum starting at n equals 2, that's the same as finding the sum where you start at n equals 0, and then just subtracting off the n equals 0 and n equals 1 terms. All right, so we'll go ahead and do that. So the full sum, if we pretended that we started at n equals 0, is given by the formula a divided by 1 over, or a divided by 1 minus r. So in this case, that would be 2 divided by 1 minus negative 2/5, so plus 2/5. All right, so now what I need to do is subtract off the versions where I plug in n equals 0 and I plug in n equals 1. All right, so if I plug in n equals 0, I'm of course going to get 2. So I have a minus 2, subtract off the 0th term. And now I need to subtract off the version, the n equals 1 term. So if I plug in n equals 1, I think I'm going to get a negative 4/5. So I have a double negative, so I'm going to have a plus 4/5. All right, and if you go through the trouble of simplifying it, you should wind up getting that this is 8 divided by 35. Okay, so I have one more for you in this vein. Let's take a look at sigma sum, n equals 0 to infinity, of negative 3 plus e to the n divided by 2 times 7 to the n plus 1. All right, so usual game. This is supposedly like a geometric series, so we should be able to write it out in that standard form. So let's see if we can do that. All right, so usual game. Let's try to rewrite every term or every factor, everything that has an n in it, so that we just have a constant to the power positive n all by itself. So I think the only factor I need to do that for is the 7 down here. So I can write this as sigma sum of negative 3 plus e to the n divided by 2 times, I guess, 7 times 7 to the n. Which I guess I can simplify slightly more if I write it out as minus 3 plus e to the n divided by 14 times 7 to the n. Okay, so now we need to go and group together everything that has an n in it on one side and everything that does not on another. So in this case, we have something a little bit different going on because we have this plus in the numerator. So it's not completely possible to just do it, to go and separate them out in the way that we're used to. But it's not too hard to see how we can handle this situation. If we have a plus in the numerator, well, we can just split the fraction apart and therefore split the series into the sum of two different series. So one thing I can do is rewrite this as, instead, n equals 0, sigma sum n equals 0 to infinity of minus 3 over 14 times 7 to the n plus the sigma sum of e to the n over 14 times 7 to the n. And both of these guys, I think we can go and group together the n's and the constants in the way that we're used to. All right. So I think this first one is going to turn into a negative 3 over 14 times a positive 1/7 to the power n. And the next one is going to be I think we're going to have a 1/14 times e divided by 7 to the power n. All right, so we have two series, so we need to check if they both converge. If either diverges, then it's game over. So 1/7, that's less than 1. We're in good shape. E divided by 7. Well, E is 2.7 something something. If you divide that by 7, you get something less than 1. So yep, both of these are convergent. And so we should be able to find their sums straightforwardly in this case. Their index starts at n equals 0. So in our case, this should be, take the a, the -3/14, and divide it by 1 minus a seventh, and then add the same thing from this side. So that'd be a, which is a 1/14 in this case, divided by 1 minus e divided by 7. Okay, so far we've been given a series and we've been trying to determine whether it converges or diverges, and if it converges, what is its sum? But now I'd like to turn to a different sort of question, a kind of backwards question, if you will, in which instead of trying to decide whether a given series converges or not, we'll be given a generic geometric series, and we want to decide under what conditions will that series converge. So as kind of an example, let's take a look at this one real quick. So this is example 6. Let's say we have a generic series, which looks like this. And by generic, it means that the terms have a variable inside of them. So we have sigma sum from n equals 1 to infinity of x to the n divided by -8 to the power n plus 1. All right, so just to be clear, the task here is to decide what values of x that we can plug in give us a series that converges. So I could plug in x equals 2, x equals 3, x equals 10 billion, and I want to decide what x values out of all possible x values will result in a series that converges. All right. Well, we know when any series, any geometric series converges. That happens whenever the r value is strictly less than 1 in absolute value, in magnitude. So one way we can answer this question is to find out, well, what is that r value? So to do that, let's try to rewrite this geometric series in the more standard geometric series form of a times r to the n. All right, so we know the usual game for that. We want to turn every factor that has an n in it so that it's just something to the power n all by itself. So in this case, that means getting rid of the n plus 1 and turning that into just an n. All right, well, that's not too hard. -8 to the n plus 1, that's the same thing as -8 to the n times -8. All right, and I won't go over there. All right, so we'll group everything that has an n on one side and everything that does not on another. So I think we're just going to wind up with a -1/8 as the constant. That's the a, times x to the n over -8 to the power n, and we can quote-unquote factor out the exponent n to give us the following. All right, so that's our a, and this is our r. All right, so now we're in good shape because we know when any series that looks like this, doesn't matter what we plug in for x, this series is going to converge if the r is less than 1 in absolute value, and it's going to diverge if anything else happens. So in this case, the r is negative x divided by 8. So in our case, if we want convergence, that must mean that we want the absolute value of negative x over 8 to be strictly less than 1. All right, well that works, although we would kind of like to rewrite this in a more human-readable form, like exactly what x values satisfy this condition. All right, so in that case, that just amounts to solving this inequality for x. All right, well, so to start off, we have an absolute value of a negative, so I don't need to write that negative. I can write this as absolute value of x divided by 8 is less than 1. If I multiply both sides by 8, I get that the absolute value of x is strictly less than 8. And if you have an inequality involving an absolute value, you can drop the absolute value if you, well, or you can drop a less than, I should say, by bounding x between 8 and its negative version. So if your magnitude is less than 8, that means that you must be in between strictly negative 8 and 8. All right, so that's our condition. As long as you plug in an x value that is strictly between negative 8 and 8, this series is going to converge. And if you plug in anything that's not strictly in between minus 8 and 8, it's guaranteed to diverge. All right, well, if it's going to converge under this situation, what's the sum going to be? All right, well, we know the formula for that. If we want to find the sum of a geometric series, that is a divided by 1 minus r, although, again, we have to be a little bit careful because we're starting from index 1 in this case, so we'll have to do a slight adjustment, but not very much. So we'll start off with just following what the formula says. We take a and divide it by 1 minus r, so it's a double negative, so I have 1 plus x divided by 8. And I need to make a slight adjustment, which is I need to subtract away the 0 term, which isn't actually there. So the 0 term would be just a negative 1/8, so I need to subtract negative 1/8, so that is the same as adding 1/8. All right, so that is the sum of our series, again, assuming this. As long as x is within this range, we know the sum is going to be that. All right, so I have one more in this vein to show you guys. So take a look at this one. I have sigma sum n equals 0 to infinity of 2 to the n plus 1 times x plus 3 divided by 3 times 4 to the n. All right, and so same question. We want to decide, well, what values of x does this thing converge, and what values of x does it diverge? Well, okay, so this is supposedly a geometric series, so let's see if we can write it in its more standard form. So we'll play the usual game. Let's go and rewrite everything that has an n in it so that it's just so that the n is all by itself. So I think that only means doing one thing in this case. So I'm going to split apart the 2 to the n plus 1 into 2 times 2 to the n times, and then everything else is just going to be the same. All right, so we'll group everything with an n together on one side and everything that does not have it on another. So I think that's going to leave us with 2/3 times x plus 3 times 2 to the n over 4 to the n. And I think that can be simplified a little bit. So factor out the n, we're going to have 2/4 to the n, or in other words, 1/2 to the power n. All right, so in this case, we've got the form that we want. That's the a, and the 1/2 is the r. So at this point, I would like to ask you guys to pause the video for a little bit and see if you can answer the question here, what values of x is this series going to converge? So go ahead and pause it and see if you can answer that yourself. No, I really mean it. You're supposed to pause now and, actually try it, I can wait. It's okay. Okay, so that wasn't so bad, was it? All right, so you might have noticed something weird is going on here. So remember, the rule is to determine convergence or divergence of a geometric series is we need to look at the r value. But in this case, the r value doesn't actually have an x in it. It's just 1/2. So r is 1/2, and certainly 1/2 in absolute value or without it is definitely less than 1, which implies convergence. So in that case, what does x have to do with this? The 1/2, the r value is less than 1. What does this have to do with x? Well, the answer is it has nothing to do with x. So what that means is the convergence of the series in this case, because 1/2 is less than 1, the convergence is independent of x. X has no influence on r. So in that case, this series converges for all real numbers x. So every value of x under the sun will work here. Seems kind of strange, but turns out it works. Basically, all that x is doing is, because x is forming a component of the a factor, really all it's doing is just scaling whatever the sigma sum of 1/2 to the n is. That's going to be some sort of finite number. Changing x just changes, well, how much are you going to multiply that amount by? All right, so this apparently converges for all real values of x. So in that case, we should be able to find the sum for any real value of x. All right, well, we know what to do. This is a sigma sum starting from n equals 0. So we don't need to do any fancy trickery with the formula. It's just going to be straight up a divided by 1 minus r. And in this case, a is going to be 2/3 times x plus 3. And we're going to divide by 1 minus 1/2. And I think if you want to simplify it out a little bit, that winds up giving you 4/3 times x plus 3. And again, that works for any real value of x under the sun.